for the opportunity. Now I will talking about this project I have developed in collaboration with my PhD students. One of him is present here, and my collaborators from Belgium and Germany. Okay, before saying my taking home message of this talk, I would like to revisit a very well-known problem in the undergraduate course, in the thermodynamics course, with the question: you have your system, and it receives an amount of heat from the hot bath, and it's partially converted into work, and one part is weighted to the cold bath. This is the typical problem you have in the thermodynamics, in the equilibrium thermodynamics. Here's, for example, you move some pistons in your systems, the pressure is changed, and you have a system performance, and it's converted into work, and you know that this efficiency cannot violate the Carnot, and you have the sequence of quasi-static process, your system is macroscopic, and so on. Okay, so now you can ask the same questions, but in the framework of nanoscopic systems. These questions has attracted the attention during the last years, and we have some similarities and some differences. What are the similarities? You can also ask the same questions to extract heat and partially convert into work, and some part is wasted, but there are three remarkable differences. First, the nanoscopic engineers in the engineering conversion does not come from moving pistons, but instead of it comes from currents from microscopic particles. A second remarkable change. Typically, the systems operates far from the equilibrium, and hence its performance is expected to be lower than the ideal case. Third question, unlike the macroscopic thermodynamics, fluctuations in these cases can become important, and hence the strategy for boosting your system performance can be crucial. Now, I will exemplify, before describing telling my take-home message, I will describe the typical setup in which you use and in which you try to answer this question in the thermodynamics. This is a typical setup. We have a nanoscale system, in this case a quantum dot, a two-level system, for example. It's placed in contact with two distinct thermal baths. The contact can be simultaneous, or one part you place it in contact with the hot and the other part with the bath, or you can also promote a time variation of your parameters, energy levels, temperatures, and so on. This is the typical setup. It can be composed of a single system or a Brownian particles, and in other words, a setup composed of a single or small systems. However, we know that the nature is plenty of complex systems, composed of many interaction systems. And a question which naturally arises is how these systems, interacting systems, displaying cooperative behavior, can be used for boosting the system performance. This is the taking-home message. This is one question I would like to try to answer, at least partially, in this talk, okay? For that, oh, I'm sorry. Okay. More details you can find in this reference, in the archive. Okay. This is the typical setup in the first part you consider. A collection of interacting particles. We have the term accounts to the interaction between when the units are in distinct states. For simplicity, you can consider several states per unit. In this case, you consider 2 or 3 state cases, but extension, generalization is straightforward. This term accounts to the interaction when units are in the same state. But the point is, in the first version, all units interact to each other, and here is the contribution of individual energy. Okay, of course, this expression is a mean field-like expression, and it grasps the cooperative behavior I would like to investigate, but it presents many independent parameters, and for this reason, I will consider some choices inspired in the Ising model, which is one of the most important model in the equilibrium statistical mechanics, which displays the cooperative behavior. Okay, so I proposed the idea, the setup, and now, okay, if the system presents a cooperative behavior, you can describe in terms of disordered parameters. In the case of Q equals to 2 and Q equals to 3. And, okay, the last information before showing my results is the work source. I described the setup, a collection of interacting particles. Now, the work source among the distinct possibilities, I will consider a simple choice in which all particles interacting to each other and each system is simultaneously placed in contact with both thermal baths, and we have a non-conservative force. Here is in the counterclockwise direction, and here in the clockwise direction, according to whether the particles is placed in contact with the cold and the hot bath, respectively. Okay. Since we are, I will pause to make a few comments in this part. We are interested in the conversion of heat into work, so we needed to introduce a work source in my system. This is the work source I will introduce. Of course, there are other possibilities, but this is one of the simplest ones. Okay. Okay, once introduced the model, the idea, the approach, and the work source, I will solve this model. This model is, I will consider a Markovian approach described by a master equation, and it can be exactly solvable according to these transition rates, and this is the framework. Mathematically, the computational procedure is to find the steady state probabilities in which they will provide the calculation of thermodynamic quantities. Okay, so if we are interested in the system performance, we need to calculate the power and the heats. So from the probability distribution, you can calculate them, and consequently the system efficiency, and we are interested in investigating the collective effects, how can be used for boosting your system performance. If in the case of the system operate as a heat engine, we have this following definition for the power and the heat. If it operates something like that, a refrigerator, we have this convention among signal of quantities, and here the system does not convert anything it receives from the hot bath. Okay, this is the efficiency I will investigate, and this is for the sake of comparison, the Carnot bound. Okay, now I will plot the main results. To have a global idea, I am going to show the heat maps of driving interaction among units. When it is strictly negative, all units operate collectively in an ordered way. So something like that, the system is ferromagnetic. So in this case, it operates as a heat engine, and you can increase whether the interaction or the driving, or the interaction, and the power can be optimized. We see that there is a central region here in which it can be simultaneously maximized, providing a maximum power. As the interaction decreases, there is a crossover here, and the system operates as a pump. In this region, for example, all units operate independently from each other. Here, collective effects are important. Here, collectives are not important. They operate independently, but in some cases, collective effects can also induce the system to operate as a pump. Okay, this is the heat map for Q equals to 3 in the all-to-all version. And here is the efficiency heat maps. It's similar, but there are some small difference. It cannot be simultaneously maximized. In other words, there is not an optimal driving nor an optimal parameter in which it can be optimized, but as you increase both, it approaches to the Carnot. Just for the sake of comparison, the Carnot bound is 0.5. Okay, so I am in position to answer my first take-home message. Collective effects, this part can boost the system performance. The robustness of these finds, for example, we see a similar behavior for Q equals to 2, reinforcing the robustness of our finds. Of course, there are some small differences here. This crossover from the regimes is from a Carnot efficiency, ideal efficiency, and an important result is the following. Okay, these results were obtained from a mean field model, all-to-all interactions. How are things beyond the mean field? In order to answer this, I consider, instead of all-to-all, now they form a regular arrangement. Interactions form a regular arrangement, something like that, a square lattice. These results for this case are symbols, and for comparison, continuous lines is the all-to-all case, and you see not only the all-to-all described is the agreement is practically the same, reinforcing not only the reliability of this mean field-like description, but also this strategy as collective effects for boosting your system performance it can be very useful for improving your system. As a last comment, we have other features I would like to show, but I will not have enough time. Okay, just a very short comment here. Collective effects, as you increase the system sizes, you improve the efficiency and the power, and as for reinforce again the power of the collective effects, and this there is the poster of my student Gustavo. He can show you in more details, and this is the conclusion. And sorry, collective effects can be used for boosting your system performance. And thanks.
Thank you, Carlos. Time for one quick question. I have one quick question for you. It's your mean field model. You're treating it analytically, or you're simulating the fully connected model?
No. It's exact. It's exact.
Okay.
It's exact.
Thank you. Okay, I'll invite my next speaker, who is Matheus Valença Correia. Okay.
My name is Matheus. I'm a PhD student from the Federal University of Pernambuco. And today, I'm going to talk to you about three-body interactions in confined clusters of particles. So this is a paper we published in the Journal of Physics, Condensed Matter this year, with my colleague, Emerson, and my supervisor, Clécio. And this is a little summary of my talk. I will explain to you briefly why are we talking about three-body interaction, how can it be applied to a confined cluster of particles in 2 dimensions, and talk about our system, our numerical study, and our findings. So you may think about three-body interaction, you may recall the three-body problem, but we're actually talking about like a correction we can insert in the system. Like for classical many-body systems, usually nearby particles which are interacting with each other, they can modify the interaction potential. So the first contribution we can insert in the system are the three-body term. We can add many body terms, 4 body terms. And so this potential here depends on, for example, the position of a given trio of particles. So this is important because it elucidates in many problems, in many systems, a lot of properties, like noble gases, neutron star matter models uses it, superconducting vortices, And also there's a cute example, which is the self-optimization problem in penguin camel taxis. Three-body forces can be used to describe this self-optimization. But the greatest example are the charged colloids, because the charged colloids, they possess an ionic, counter-ionic cloud around each charged colloid. So if we have like two charged colloids interacting, a third one can visualize this by the physical mechanism is the redistribution of these counter ions. So a third nearby charged colloid emerges a third three-body term, attractive three-body term in this system. Usually they repel each other via the Yukawa potential, but it is directly measured that there are three-body attractive interactions in these suspensions. So we want to consider three-body interactions in a class of systems which is very studied, which are the confined clusters of particles. We have a lot of systems which, in sufficiently low temperature, they crystallize into the Wegener structure, the Wegener crystal. It's a well-ordered state. And if they are confined, they can exhibit like this concentric shell pattern, which is very dependent on the confinement we adopt and the kind of potential interaction. And we can change this structure, for example, by adopting a non-monotonic interaction. So we have the confinement, a repulsive potential, and maybe some attractive part, giving rise to these complex patterns here. So we can label these states for these interacting particles just by giving the number of particles in each shell. So the idea here in our study is to consider for the interaction potential, a parabolic confinement, a repulsive potential, which we use up to 3 functional forms, the logarithmic, which is present like in superconducting vortices in thin films, the Yukawa potential for lambda equals to 1, the charged colloids, and the Coulomb potential. And the novelty here is this three-body attractive potential. We know that in superconducting vortices, in charged colloids, these terms are attractive, but we don't quite know the functional form. So we adopt a single Gaussian model here, which dependent only on the position of a given trio of particles, and everything is fixed. The confinement, the two-body potential, and we only change this parameter here, the strength of this three-body interaction. And we want to see what changes in the shell structure we can observe by doing this. So the numerical details, we basically run molecular dynamics simulations. So it's overdamped dynamics and a normal mode spectrum analysis. For a small number of particles, we can also create like a single shell model, which we assume that the particles occupy the vertices of a polygon. So we can parameterize the potential with like the radius or the side of this polygon, and then minimize the potential. So here are some results. For the single shell configuration, so for a small number of particles, we observe like these polygons, which is quite similar to the case when we don't have the three-body interaction. But there are some news because we observe a density transition. So we are inserting attractive potential, so we expect the system to compact. And this compaction happens in 2 ways. For a small number of particles, there's like a crossover in when we, this is the radius of the cluster, when we increase the three-body interaction, there's a softly shrink of this cluster. But when we increase the number of particles, and depending on the two-body potential we are using, there's a discontinuous transition here. So even in the logarithm potential for 7 particles, we have this abrupt compaction of this cluster. Besides these density transitions, we have structural transitions, which are the migration of particles in the shells. So we have a certain range of a parameter in which there's a migration from the pentagon for the square with a central particle. Then it goes back again to the pentagon, but now collapsed. And another feature of this system is that, imagine you turn off the confinement. So, oops. If you turn off the confinement, you expect to have no cohesion of the cluster, so the particles goes to the infinity. But when the three-body interaction, which is an attractive potential, is strong enough, we have a minimum here, so only by considering the interaction potential, these clusters are self-sustained. So the density transition, which I was talking about, is the jump of the system from this minimum to this minimum, so we observe this abrupt compaction of the cluster. So in the normal mode analysis, we have some hints on what happens, because there is a softening of the breathing mode approaching the transition line. So we have some information about these transitions, not only the crossover, but also the discontinuous transition. In this case, we changed the two-body potential strength, but it was only in this case. And for multi-shell configurations, what happens when we increase the number of particles? Well, basically the same happens, but now we have more abrupt transitions, because if you see here at the numbers, we have also the density transition. The cluster also collapses, but there are more accessible states for it to fulfill the shells, so we can break like this the magic configuration, the 1,612 into 1,711, 2,710, and then it goes back to 1,711. And as we increase the number of particles, of course, we have the same behavior. So in a summary, we can construct a phase diagram comparing the non-compact and the compact clusters. These transition lines are different for each two-body potential because of the difference in the range of these potentials. We see here the closed circles as the abrupt compaction, and the open circles as the soft compaction of the cluster along a given range of our K3 parameter, the intensity of the three-body interaction. So we have basically these three effects, and I think I'm done. Thank you very much.
Thank you. We have time for questions. Hartmut.
You mentioned charge colloids as one example for triplet forces, right?
Yes.
There you know it's a superposition of Yukawa potentials. So you could take the more realistic form instead of the Gaussian approximation.
Yeah.
It's a comment. So.
Yeah, we think.
But I like all the multiple results here, all the structures are very nice.
Thank you.
Lucas.
So you have kept the temperature 0 in the dynamics, or
I forgot to say that. We run like a simulated annealing scheme. So we begin with high temperature. The system is virtually liquid. Then we decrease the temperature to reach equilibrium configurations. We also observe like metastable states, but we focus on the equilibrium configurations.
Okay, let's thank Matheus again.
I want to thank the organizers for setting up this very nice workshop and for the opportunity to share our results here with you. This work has been done in collaboration with Alejandro Mendonça Couto, Valera Matiello, Romulo Sensi, and Nicolao Defeno. So we are interested in describing two-dimensional melting in particle systems. We know that in two dimensions, systems described by continuous variables present a low temperature phase that is characterized by a quasi-long range order, where correlation functions decay algebraically in space. And what Berezinski, Kosterlitz, and Halperin, Nelson, and Young showed is that the topological defects play a special role in these phase transitions to a disordered phase in higher temperatures. So this theory is a renormalization group theory. In this sense, it describes the universal properties of these phases, but it misses the non-universal properties like the critical temperature. On the other hand, mean field-like approximations fails completely in addressing the correct nature of the low temperature phase because it usually assumes a long range order in the low temperature of the phase. So what we are trying to do is to combine mean field approximation with the renormalization group theory to give a quantitative description of the phase diagram without missing the correct nature of the low temperature phases. We have done this previously in pattern forming systems and in the XY model. And in this work, we are trying to describe the melting of the 2D solid phase of the Gaussian-core model. So the program of the work is to treat smooth fluctuations in the ground states using a self-consistent harmonic approximation, a mean field type approximation, where we can obtain the elastic properties as a function of temperature, make good estimates of the energy of the defects, and with that, we can plug both of these into the renormalization group equations and describe the phase transition and the critical temperature more properly. And we check the consistency of these results with the numerical simulations. So the Gaussian-core model is a soft-core repulsive interaction, a pairwise interaction. We want to study the melting of the solid phase, so we write the problem in terms of the deformation field around the equilibrium positions of the particles in an hexagonal crystal. And we start off with a variational free energy with the Bogoliubov inequality with the tri-Hamiltonian that's harmonic in the longitudinal and translational deformation fields. So what we would do, what we do, is to determine the functions f1 and f2 variationally. Actually, so this is a long calculation. We determined the quadratic coefficients of these functions self-consistently, and these are related to the Lamé coefficients of these systems. So, for instance, let's see the shear modulus. We see that when it drops suddenly to 0 is when we have a transition to a liquid state. Here we can also see that for moderate densities, we have higher critical temperatures than for lower or higher densities. Okay. So now to estimate the core energy of a dislocation, of the topological defect, we start off with the Halperin-Nelson interaction energy between these dislocations. This interaction energy is written in terms of Burger's vectors density field. So what our model does is to start with a microscopic configuration setup for a pair of dislocations and make a coarse graining of this pair of dislocations. Then, okay, so we use an important input from simulations at 0 temperature, where we obtain that the minimal distance between these dislocations is around this value, where A is the lattice parameter. At the end, we arrive we estimate the core energy of a dislocation as half this interaction between pairs of dislocations, and it depends only on the Baire-Young's modulus. That depends on the Lamé coefficients we've calculated earlier. So now we have the core energy of a dislocation and the Baire-Young modulus. We can use both as initial conditions for the renormalization group equations of the classic paper on two-dimensional melting of Halperin and Nelson that describes the renormalization flow of the Young modulus and of the fugacity of the dislocation. So since the initial conditions depends only on the Baire-Young's modulus, and the transition is characterized when the Young modulus, the renormalized Young modulus, arrives at a value of 16 pi before dropping to 0 at the higher temperatures. And this is the fixed point of this flow, let's say. We can map this condition for this transition uniquely into an initial condition, which is this. So we can identify either the transition by running the renormalization flow equations, or just looking at the initial condition, which depends on the temperature, that is the Baire-Young's modulus. And it takes this value of 23.9 pi. So we want to check these results with the molecular dynamics. We estimate the translational and orientational order parameters. We measure their susceptibilities, extrapolating the values for larger volumes or number of particles. We arrive at this numerical phase diagram. We see the two-dimensional solid phase, the exotic phase, and the fluid phase. We are interested in this purple, the two-dimensional solid phase transition. And this is our main result. So we can see here in the black dots the simulation, which is almost like the experimental result in this problem. The self-consistent harmonic approximation in green, and in orange, the combined approach using a model for the energy of a dislocation. So we can see that the combined method of combining mini field and renormalization group describes very well the phase transition and the phase diagram. An extra consistency result that we do is to check this condition for the Young modulus. So we know that we can measure the Young modulus from unperturbed equilibrium distances in a traditional method. We have the elastic constants that depends on the Born term and on fluctuation terms of the stress tensor. And we can estimate the Young modulus, okay, by the shear and the bulk modulus. And we see that the full, let's say, Young modulus, the criteria of the two-dimensional melting theory of 16 pi gives, in these orange dots, a good estimation of the location of the transition. But also, if we suppress the fluctuation terms, and if we interpret this as the baryon modulus, then also the condition we arrived analytically also gives a good estimation of the phase transition. So that's it. We have a very good accurate results. We see that the temperature drops significantly when we turn on the randomization group because of the relatively low energy of the dislocations, so it proliferates at low temperatures. And that's it. Thank you.
Questions for Lucas?
So you showed this phase diagram with the reentrant
Yes.
behavior for high densities. So is there always a Higgs-static phase also on the left wing of the phase diagram?
Yeah.
If you can go back,
Yes.
maybe a couple of slides.
Yes.
Yes. So on the left part,
Yes.
where you have fluid and is there a Higgs-static phase or not?
Yes, but it's
very small?
It's very small. Yeah.
Since I would expect it to go somehow to the hard disk limit, yeah. If this
But
KBT over V naught is very, very small.
But this is a very soft model, so the particles can, without any cost, be in top of each other.
But if V naught, if the prefactor is very large, it's getting harder and harder. Then you see the wing of the Gaussian. Yeah? For high densities, it's getting softer and softer. And you could
but for low densities as well, because the force, the repulsive force is 0 at the core of the particle.
But you are at densities where you have distances, 0.1 in sigma, so you don't feed the overlap. And then it should be harsh. It should be harsh, the potential.
Mm.
So in this limit, you should hopefully get hard disk behavior, which is known in one first order and one second order transition between liquid and Higgs-static.
I don't know about that because it's a very soft core. If you see the potential, at small distances the force is 0. So the force goes like this, the repulsive force. So it's 0 force, repulsive force at short distances. So there's no hardcore limit here.
Yeah, but maybe an effective hardcore.
But
which in the Barker-Henderson theory, you use that exactly.
Yeah, but I don't see this happening. Maybe you can talk more, but I don't understand very well. But thank you. Yeah.
Okay, let's thank Lucas again.
Thank you. First of all, I want to thank the organizers for this kind of invitation and the opportunity to talk here and share our investigations in Córdoba. So, first of all, as Danilo said, I will talk, let's see, about interaction, dipolar density interaction between disks. So first question is why disks? And just as a motivation, the origin of this the problem starts from the biological membranes. So as we heard this morning, these are made by phospholipids, and these lipid cells can either form micelles, bilayers, or lipid monolayers. And as also we heard this morning, the biological membranes are quite complex, and one of the characteristics that we are interested in describing is the fact that they exhibit domains that are rigid phase that diffuse in a more fluid phase. And these are quite important in biological relevance, for example, for membrane trafficking, signaling. So it is interesting to capture and understand the behavior. Also, an example, interesting example for monolayers, for lipid monolayers, is in the case of the lungs alveoli. There we have a monolayer which is presumed to have also domains which are responsible for avoiding the collapse of the alveoli when we exhale. So it's also an interesting example where we have a biological monolayer. Let's see. Have some delay. Okay. So again, the problem's quite complicated, as always, reality, and then experimental setup to try to mimic this and study this in a more synthetic and versatile way is the Langmuir monolayers. Here's an example from Langmuir balance, where they put just a monolayer of phospholipids, and picking the right combination of lipids and the right place in the phase diagram, you can have a coexistence between two phases, a liquid condensate and a liquid expanded. And the liquid condensate form this almost, I would say, circular, for my interest, domains which are suspended and eventually interacting, as we see in this picture. So we are interested in the interaction between the domains because the interaction will explain the structure of this monolayer. In some sense, for us, will be like a colloidal suspension of two dimensions, actually. But let's say, what about the interaction? Okay, the main interaction between these domains is or arises from the fact that these neutral lipids have a dipolar moment. This dipolar moment is product of the structure of the molecule and also for the hydration, because the part of the molecule is in water. And so if we have two phases, the more concentrated phase, the condensed phase, has larger dipolar density than the other phase. So the interaction will be, or will arrive, or because of the excess dipolar density of condensed phase in comparison with the expanded phase. So for us, then what we end up having is a set of disks, because we will approximate as disks the domains, and in principle monodispersed disk in this case, and they interact by some surface the dipolar density, which is in this surface. And to calculate the interaction potential, it's just electrostatic. You have to integrate over the two, in the case of two disks, at the distance r, you integrate over the surface. And in principle, it's a four-fold integral, but you end up with a one-fold integral with elliptic functions. It can be done numerically, not so difficult. So we will use this, and what we will do in principle, we have done, is with this potential, with the Brownian dynamics, molecular dynamics, and eventually what I will talk about today is some integral equations. So just to keep in mind, the potential has some interesting limits. One of them is that it goes to a constant value at contact, and in our simulations and also in the theory, we will put some hard core, so we want them to get just into contact, and the potential goes to infinity. So at contact has a finite value, but the force diverges at contact because it is a square root. And in the other limit is what we expect is the point dipolar limit, which, by the way, has been studied already in the literature. So since this has been studied, it's interesting to note here is a plot of the interaction potential versus distance. This is contact, and this is a log scale, where the typical distance here is about 5 radii. There's still an important difference between the point dipole limit and the exact density dipolar potential. So we expect that our results will not be exact or not quite similar to those of point dipole. So what we will look in, since we also have done some experimenting in collaboration with the chemistry faculty in Córdoba, and our collaborator was Bilke and Rafael Fiore. They did experiment, and what they measure is the pair distribution function. I hope you know it. This tells you the probability of finding a domain at a certain distance r from another domain. This is a typical picture. You sit on one of them and count how many neighbors you have, and you get, for a liquid state, something like that. And also, not so easy accessible from the experiment, but you can Fourier transform this and get a structure factor, the static structure factor, which is also interesting to compare or analyze. So that's what we got for the first case. We have fit the experimental results, looking for the density, the dipolar density here in the potential. I didn't mention, but you have here the dipolar density to the square, which is this actually this F naught. There is dipolar density over the effective permittivity. So experimentalists are quite interested in knowing how this dipolar density, which value it has. So what we did is we simulated and fitted the experimental results to the simulation. Here, simulations is the blue line. And having this fit, then we can get the dipolar density, which, by the way, got to relative good agreement with what the experimentalists expected. And furthermore, we also made some working curve for experimentalists so that if you have your packing fraction, here different colors are packing fraction, you know, you measure in your experiment the peak height of your pair correlation function, and from there you can get the if naught, which is actually the dipolar density. So this was quite successful, even though we have to keep in mind that polydispersity is actually very important, probably, and we have also studied the effects of polydispersity. I'm not going to comment on this now, but you can find this in this reference. Knowing this, we were interested in finding a way to, since this is, if you are not happy with this working curve and you want to be more precise, like here, which this fit costs you many simulations, fine-tuning the if not value, so the density, the polar density, until you match the peak height. So this is numerically involved. We are planning, or we wanted to do it with theory instead of simulations, with the integral equation theory. So we decided to see how this numerically can be done. And for this, let me first introduce some reduced units, which is convenient. We introduced the mean interparticle distance, which is the square root of the particle density, the number density. In these units, the dipolar density potential, just from the 4 parameters we had, temperature, if not density and radius, end up with just 2 parameters, a coupling parameter, which now depends on the mean interparticle distance, and volume fraction, or area fraction, actually. You end up just with 2 parameters, and using this, you put this in the Orton-Cernick equation, which is an integral equation for actually the correlation function, the direct and total correlation function, which are related with the radial distribution function. And you need a closure condition to solve this. In the closure condition, you have the potential you know, and these are the unknowns, And you have also an unknown function, which is the break function. This is where the approximation enters. You have to propose different break functions, and you end up with this with different closures on different schemes. The most common schemes are Perkins-Yevick and hypernetic change, and mixed schemes like Rogers-Young and variational modified hypernetic change. I will skip, just want to mention that we will pick just 3, the Rogers-Young scheme, which was already used for point dipolar, and the modified hypernetic change, and the variationally modified hypernetic change. These schemes all have a mixing parameter. Here is an effective volume fraction or area fraction of the reference system. And just, I will jump to the results. What we obtain is here just for just one volume fraction, area fraction, which is 15% over there, and incrementing the coupling parameter from 0.5 to 0.6, and what is more important, from low structure to high structure. And we see that, in principle, all the schemes perform very well, extremely well, I would say, except for the Rogers-Young schemes, which for low interactions or for low structure systems works very well, but for high structure systems, there is Rogers-Young here, and the violet is not so good. And so here it's also not giving the right right medium over there. So this is also the result for the structure factor. We see also more or less the same. Rogers-Young has a poor performance in principle for highly concentrated systems. Otherwise, all other systems perform very well. There are some advantages of one over the other that you could find in the reference. I don't have time to go into the details. And if I have 30 seconds more, I will tell you something about the isomorphisms, which is a property of strongly correlating liquids, which this is the case of this interaction potential that we have. Strongly correlating systems are those which you have scaling the position of the system. These are the particle positions. If you scale them with the square root of the number density, you get the same Boltzmann factor. So you end up with the same entropy, the same correlation functions. Everything is mapped, so you end up with, instead of a 2D phase diagram, just a 1D phase diagram when you have isomorphic curves. And we tested this for our case, and we find that these green lines are isomorphic curves, and this, the color is the height of the peak of the per correlation function. And in this line, the red ones is we measure the peak 3.01, and the green line is obtained within the formalism of this isomorphism. So it works quite well. And okay, this is what you see. These are the per correlation function along this line. And if you map them with this reduced unit, they fall all on top of each other. You have to zoom it a lot to see that all the lines are over there. So I will finish here, and I'll let you read the conclusions so that we are not too late for dining. Thank you.
I have one comment about the discrepancy that you're showing in one of those plots for G of R. And if you think that's not good, I mean, for almost everyone will agree that this is pretty good, even though
That's great.
Yeah. Anyway, are there questions?
We are old liquid state theorists. So we know all the structure factors look like that. All the G of R's look like that. So little differences do matter.
Yeah.
I mean, we know this from our early days. So it's fine. It has to be careful.
Yeah.
I mean, I have another comment. So you could, if you take the logarithm of G of R at low densities, you can, this is the potential of mean force.
Yes.
Can you extract that from the experiments to see whether your density dipolar model is good or better than the point dipolar model? I mean, this is a way to measure the interaction forces by the pair correlation.
We have thought this is the experimental results.
Of course, this is you have already neighbor peaks, and then you need really high dilution for this. Okay, but you need even smaller phis.
Yeah, this is not so small, 20%.
I see.
And what we are trying to do is, if we get after we did the integral equation theory, is probably we can do the inverse of Cernic and see what we get out. But then you play what bridge function you use. But we would think if the bridge function is good for point dipolar or for this density dipolar, and the interaction potential is similar, then should be also good for the true one.
But you are saying the point, say the hard disk point dipolar and the hard disk density dipolar.
The hard disk density.
They're really different.
They're different.
They give a different G max.
Yes.
Okay, good. Yeah.
They only are similar at the low density limit. In the low density when they get far apart. Because
yeah, then it doesn't matter. Then you see just the long distance behavior. Yeah.
right.
At high density you make
yeah.
I have maybe a naive question. When you showed the Langmuir isotherms,
I don't know.
in the first or second slide,
Yeah.
maybe. You have there a mixture of lipids.
Yes.
In order to get these
In order to get this, I'm not.
clusters, it's
Yeah.
only when you have mixtures, not for a pure.
Not for a pure. I'm not a specialist, but I have here maybe this answer you something. There it is.
Yes.
This is a DSPC, 50%, and the DP, where is it? So yeah, it's a mixture.
And
DSPC and the MPC. Whatever this means.
They have different transition temperatures.
Like,
Gel fluid.
yeah, I guess so. But I'm not the specialist on that.
Okay. And the second naive question, your integral theory, you said Perkozievic, it's for hard disks? No.
Yes, Perkozievic is good for hard disks. And actually, one of the points that makes a little difficulties in 2D is that hard disk in 2D Perkozievic has no analytical solution, but in 3D it has. That's why hard disk is usually used as a reference system. And we also use hard disks here and Perkozievic for the reference systems.
Okay.
Right.
Thank you.
Okay, let's thank Professor Adolfo again.
Thank you.
Last talk, we can do it. Then we have some nice barbecue. I assure you this will be quite fun. We have been cooking this thing for quite some time, and we got some nice results. So today I'm talking to you about auxetic metagrains. This is not a work I've done only by myself. I've done mainly with Dan Hafer, who's from University of Amsterdam. He did the experiments you'll see, and I did mainly the numerical simulations you'll see. Of course, Gustavo is working this too. He's from PUC, and you saw him doing a presentation before, the best post ever. And then you have Sharam, Eden, and Corentin, who are from University of Amsterdam. Well, an outline of what we'll see. First, I'll explain you a little bit of what are auxetics. Then I'll explain you how we make auxetic grains and how we simulate these auxetic grains. And lastly, we'll see some results about them. So firstly, what are auxetic materials? Well, it's quite hip nowadays to talk about auxetic things. Only cool kids are working on it. But if you haven't heard about it, I'll give you a small talk about it. So the best way to see them is to compare them against a common elastic material. So you take any elastic material and you stretch it, it becomes thinner as you stretch it, as you can see in this rubber band or in pizza. But in contrast, auxetic materials, if you stretch them, they become thicker in the opposite direction. Or if you compress them, they become thinner in the opposite direction, which is quite weird. We characterize this property through a number we call the Poisson ratio. If the Poisson ratio is positive, then it means that it's not auxetic, and if it's negative, then it is auxetic. The Poisson ratio is quite simple. It's just the ratio between the deformation in one direction against the other. Some numbers for you to have. The Poisson ratio is 0.5 in rubber. It's 0 for cork. That's why cork is so good for tapping wine bottles, because it doesn't expand in the other direction. And -1 will be if it expands in all directions or compresses in all directions equally. Okay? They have multiple applications, from auxetic foams, toys for kids, mechanisms. There's even clothing, auxetic clothing for kids that grows as your kid grows, so you don't have to buy too much clothes. And at Universidad de Chile, we developed at some point a robot that crawls through an auxetic mechanism. It was quite a fun caterpillar. So what we're here for, how do we make an auxetic grain? Why we want to make them, of course, is just for fun, mainly. We want to know how, mainly we want to know what will happen if we make an auxetic grain and how they will behave collectively, what will happen with a packing of auxetic grains. But how we make one of them was quite a challenging question at the start, but we solved it firstly by starting from a common auxetic design. In this case, we use this reentrant auxetic. And we looked at its unit cell, which is right here. And we took one single unit cell that behaves auxetically, so you compress in one direction, compress in the other. And we just drew a circle on top of it to have an idea of how it looked. And from there, we got the main idea of how we design our auxetic grain. But it wasn't as simple as this. Dan went through many different designs that all actually failed to behave auxetically, until he came with this design that did behave like an auxetic. You can see you compress in one side and get compressed on the other. He was quite happy of his achievement of doing this. It took him like a year to get to it. They're quite small, they're about this size when printed, just so you know. Then the other question is, you can see that if you compress a group of them, we should design some, we call them regular grains, which if you compress them, they just compress like pancakes. So if you compress regular grains, the contact between them becomes stiffer as you compress them. Meanwhile, auxetics lose the contacts while you're compressing. Furthermore, we show that effectively these grains do behave like an auxetic if you compress them in any possible direction, because they have a small anisotropy. Now, the other question is how we make auxetic grains, but not just in the lab, but how we model them or how we perform numerical simulations with them. We wanted first to create a numerical model where we could tune the Poisson ratio of our particles. We too wanted the software to be simple and run fast, and to have a defined potential energy. So just to be simple, firstly, we started working with ellipses, with the most simple particle that can show deformation. And the ellipse has 5 degrees of 5 degrees of freedom. 2 will be of the formation of the semi-axis A and B. Another one will be the orientation of this ellipse, and The other two would be the translation of this, of the elliptical particle. And to guess how to build this potential, we asked ourselves the main questions of what we want from a regular grain. Well, mainly a regular grain behaves in such a way that it is hard or it is difficult to change its area, but it's easy to change its shape. It changes to a pancake. And meanwhile, an auxetic grain doesn't change its shape. It remains like a circle all the time, a perfectly auxetic grain, but it is easy to change its area. So with these thoughts in mind, we designed a potential which first had an overlap energy or a volume exclusion energy, just from the overlap of two ellipses. Secondly, it has an area energy, which is an energy that tries to restitute the original area of the particle. So if you deform it, it wants to go back to its original area. And thirdly, it has a shape energy that wants a particle to remain in its original shape, which in this case is a circle. And this epsilon here, it's a form of linear eccentricity. Now, playing around with Ka and Ks, which are the stiffness of the area energy and the shape energy, we can achieve particles that only want to change their shape and don't want to change the area, like regular particles. And we can achieve particles that only want to change the area and don't want to change the shape. So effectively, we are controlling the Poisson ratio of the particles. And we can get all the range in between of different particles with this really simple model. And we even tested it for different ratios of Ks and Ka. I showed that we got different values for the Poisson ratio, and we can control the Poisson ratio that we get. So now that we have a grain in the lab and a grain in the computer, we started working what we really want, which is looking at the collective behavior of all these particles. So first we did a bulk compression. We did a biaxial compression of these particles. And we found effectively that it is much more difficult to compress common grains in bulk than auxetic grains. This is reasonable because auxetic grains want to change the area or want to reduce the area. Meanwhile, common regular grains that deform like pancakes don't want to change the area. So they are much stiffer when you compress them biaxially. We find exactly the same when we perform numerical simulations. By the way, the numerical simulations that you will see are quasi-static simulations and frictionless, just in case. Now, we did the second most common test that you do with any kind of grain, which is shearing them. We had a Quetzal setup, which is this one. And we see that the shearing, and we have we try to replicate exactly the same setup through numerics. Only in our case, our system is frictionless. And we see that the shearing modulus in both cases doesn't change even though you change the auxeticity of the system. So for auxetic particles or for regular particles, you get about the same results for the shearing modulus in these systems. You may get the same results for the mean behavior in shearing, but we get different results when we see shearing fluctuations. So in this case, here we are shearing the particles, and I'm plotting the difference of contact forces between one iteration and the next. And we can see that the avalanches that are generated in the auxetic systems are smaller, and many more of them, than in the regular system. We did some statistics around it. And here, this IPR is the inverse participation ratio, and this is the contact force difference. And we see that in the regular system, we get longer tails, meaning that we have bigger avalanches in the regular materials compared to in the regular grains compared to the auxetic grains. This happens mainly because the auxetic grains like to shrink, and when they shrink, they're able to shift around and create many more small avalanches instead of one big avalanche. They're able to disperse energy before they gather energy into a bigger avalanche. We see some similar result when we put these particles into a hopper. If you take a hopper and you put these regular grains on it, and you compress the hopper, the system will jam, and the particles won't be able to go through the hopper. But if we do exactly the same with auxetic grains, the auxetic grains are able to flow through. We even tried mixing them. Here we have a mix of auxetic grains and regular grains, and they're able to go through too. The main reason why we observe this behavior is because of what I showed you before. When you compress regular grains, the contact between them gets stiffer and stiffer. Meanwhile, auxetic grains lose the contacts and form new contacts. This makes the arc that is formed at the bottleneck of the hopper to become stiffer and stiffer for regular grains, but in the case of auxetic grains, it just loosens immediately. So you see some flows. You could imagine that you could put maybe some of these grains into a silo, and your silo wouldn't jam or something like that. As a summary of what we have seen, we designed 3D printed robust auxetic metagrains. We developed a promising and simple model for the formable auxetic grains. We saw some auxetic grains packing properties, like they have, of course, low bulk modulus. They have similar mean shearing between regular and auxetic grains, but different fluctuations between them. And they can unjam under pressure. In terms of the outlook, we want to see what will happen in terms of impact properties, if they have interest in dissipation properties, for example. It will be really interesting looking into the jamming transition in auxetics. Who knows what will happen there? And of course, we're looking into 3D auxetic grains. And if you are an avid reader of arXiv, tomorrow it comes out. Search for that title if you want to read it. Questions? Thank you.
For the very beautiful talk. And I was really wondering about the unjamming transition that you would expect when you compress the system of these auxetic grains. And do you expect some sort of symmetry between jamming and unjamming? For instance, if you start compressing regular grains, they jam with a certain universality class or something like that. And if you start compressing and auxetic grains, would they unjam with some sort of symmetry related to the going forward or backward?
Truthfully, I have no idea what will happen around there. Yeah, I have like two completely different thoughts. One is that probably they could be exactly the same because the particles are not deforming or nothing. But they still have this auxetic, probably an auxetic mode behind them that drives the system close to the jamming transition. That could be relevant, and that could make a difference between both systems, between regular and auxetic grains.
Okay.
Yeah.
Thank you. More questions? Okay.
Thank you for your talk. Auxetic material, they're auxetic only in one direction. I think you mentioned that they are auxetic in what direction? Or
these ones are auxetic in all directions, though they are more auxetic in one direction in particular.
Okay.
Yeah,
but it looks anisotropic, the pattern that you're it seems that if you rotate it, it would be a...
Yeah, the auxeticity is anisotropic, so it's Pac-Man. If you compress it with the phase going that way, it will be a Poisson ratio of -0.7. But if the Pac-Man has the phase up, you won't be able to compress it. But if it moves a little bit, you'll start seeing like a Poisson ratio of minus 0.1. But it averages out into like minus 0.5 for the particle.
But then the Poisson ratio of a normal material is not you don't care about the orientation, but for auxetic you have to care. Is it like fundamental restriction or
no, not
just
at all? Not at all. It's a restriction of the particle that we built. Dan tried building particles that didn't have this anisotropy, but it's quite difficult. If you make 3D particles, there are some called Buckley-balls, I think is the name. The one that showed that toy, for example, that big toy, the hover-mounted sphere, that one's kind of isotropic, in my opinion.
Okay, thank you.
Okay, let's thank Daniel again.
Thank you.
Thank you all for these 2 days, for being